On June 25, 2003, France celebrated the grand opening of Terminal 2E at Charles de Gaulle Airport in Paris. However, an engineering catastrophe would turn jubilation into mourning before its first anniversary. Terminal 2E was part of a projected state-of-the-art four-terminal hub for Air France. It was being built to handle up to 17 planes at once and 10 million passengers a year. Aéroports de Paris, or ADP, the airport authority for the Greater Paris region, in collaboration with Air France, spent almost $1 billion to build the innovative structure, made to show off French engineering skill and panache.
It's just a joyous space, and you need a joyous space when you're coming off the transatlantic flight at 7 a.m. and you're going to be in the airport for a few hours waiting for another flight out. The architecture matters.
A structure with no interior columns, the futuristic tunnel was admired by many, including travelers and workers who arrived at the terminal on May 23, 2004. 11 months after opening celebrations. Suddenly, several tons of concrete, steel, and glass collapsed as a 98-foot section of Air France's boarding lounge roof fell in.
It's very long, but it's also huge in the span. It's nearly 100 feet wide. The concrete on one side slid off the support and fell to the ground. On the other side, the concrete literally flattens the roof of the oval, comes to the floor now, sits on the floor there. Huge amount of concrete. Remember, we are talking 1 foot thick concrete. So that's a lot of weight. That's 60 pounds per square foot.
When the heavy concrete roof crashed, it killed 4 people and injured 3 others. The collapse astonished many engineers and designers. Just months before, the terminal had been praised for its technical prowess. How could it fail? Clues lie in the startling design. The roof of the boarding lounge consisted of a concrete vault, pierced with openings to allow light to pass through, and an exterior metallic structure on which the glasswork was fixed. Pillars supported the entire construction. The oval-shaped structure sat inside a glass shell, where the temperature and environment were constant. The glass encasing rested on tensioning cables that kept the oval from bulging out.
It's a structure that gets stronger the more you press on it. And the classic compression structure that people know about is an egg. If you think about an egg, very, very thin shell compared to the size and weight of the egg. And yet it's actually pretty strong. It takes some work to crack that egg. On the other hand, if you get an egg that has a crack in it, that did develop a crack, it's very weak structure.
On this unusually cold May morning, the terminal's concrete structure was extremely fragile. Prior to the collapse, the temperature dropped sharply from 77 degrees Fahrenheit to just 39 degrees. The cables are exposed to fluctuating outdoor temperatures that cause them to expand and contract more than the concrete. On a hot day, the cables expand and slacken, reducing structural support and increasing the likelihood that cracks will form.
Now comes an evening after a hot day. The cable suddenly cools down. We know that just prior to the collapse there was a massive drop in temperatures. The cable shortens. What happens when the cable shortens? It wants to straighten out. It cannot straighten out because the struts are holding it in the position where it is. The force in the struts is increasing dramatically.
But the concrete was designed to handle the extra force from the struts.
But when you start dealing with those changes in the forces in the strut that I described to you, related to temperature, related to the concrete now, when it cracks, it becomes much more flexible, so it's no longer the rigid structure. The strut punches through, the concrete shell loses its support and goes flat. And that's what happened.
The perfect eggshell was further compromised by necessary structural elements of the terminal.
In the section that collapsed, you have three very large entryways right next to one another, three protrusions that mar the perfect smoothness of the shell.
That disturbs the symmetry of the structure. No longer can the structure redistribute the loads freely. If one area gets slightly overloaded, you have perfect symmetry, it will shift the load elsewhere. But if you have those sharp discontinuities, such as a hole cut in it, that's no longer a nice and self-adjusting oval symmetric structure.
In February 2005, 20 months after the collapse, the French Minister of Transport released the findings of an administrative investigation. The report stated that the structure had been slowly deteriorating since its inauguration in June 2003.
And they were very, very careful about spreading blame. That, well, the metal wasn't quite right with the concrete, the foundation wasn't quite perfect, the design had a few little problems in it, but almost certainly the failure started where the shell was pierced massively from the side.
In May 2005, ADP announced that it would rebuild the damaged roof of Terminal 2E. Pierre Graff, president of ADP, said that the only way to ensure passenger safety was to replace the entire curved roof shell. The completely renovated Terminal 2E is slated to reopen later in the decade and will cost an estimated $195 million. Terminal 2E was designed by internationally renowned French architect Paul Andreu. Coincidentally, he also designed Terminal 3 at Dubai International Airport, which collapsed during a construction accident on September 28, 2004. Engineering disasters will return on Modern Marvels.